Why does it cost so much to move a 300-foot superyacht? Imagine standing on the aft deck of a 300-foot megayacht. You are floating on $200 million of precision steel, custom marble, and high tensile glass. To the untrained eye, this vessel is the ultimate symbol of effortless, frictionless luxury. But beneath the waterline, a brutal physical battle is taking place. Right now, this 9,000-ton vessel is sitting in seawater. To move it forward at just 16 knots, its dual diesel-electric engines must generate over 15,000 horsepower. Every single second, the hull must displace thousands of tons of dense ocean water, fighting fluid resistance, wave-making drag, and turbulent friction. The cost of winning this physical battle is staggering. When a 300-foot superyacht pulls up to a commercial fuel dock, it isn't filling a gas tank. It is executing a full-scale industrial bunkering operation. It will swallow over 60,000 gallons of low-sulfur marine gas oil. At average global bunkering rates, a single fuel stop costs well over $100,000. And if the owner decides to cross the Atlantic at top speed, that entire $100,000 tank will vanish in less than 4 days. Why does moving a floating palace require the energy equivalent of powering a small city? To understand the terrifying economics of the ultra-wealthy, we have to look past the infinity pools and helipads and dive into the fluid dynamics, mechanical engineering, and sheer physical brutality required to push a 300-foot superyacht through the sea.
To understand why superyachts burn so much fuel, we first have to examine the medium they move through. Water is roughly 800 times denser than air. When an aircraft flies, it primarily fights air resistance. But when a vessel moves through water, it encounters three distinct forms of hydrodynamic drag: skin friction, eddy resistance, and wave-making drag. Skin friction occurs as ocean water rubs directly against the painted steel hull. Even on a perfectly smooth, newly painted vessel, microscopic boundary layers create continuous resistance. Over time, tiny marine organisms build up on the hull, a process known as biofouling. A layer of microalgae less than 1 millimeter thick can increase hull drag by up to 15%, burning thousands of extra dollars in diesel every hour. However, skin friction is minor compared to the main obstacle in naval architecture: wave-making drag. As a vessel pushes forward, its bow forces the water out of the way, creating a bow wave. At the same time, the displaced water fills in behind the stern, creating a second wave. As the yacht speeds up, the distance between these two waves increases. Eventually, the vessel reaches a critical physical threshold known as its theoretical hull speed. Hull speed is defined by a simple mathematical law dictated by the length of the vessel at the waterline. The formula states that maximum displacement speed in knots is roughly equal to 1.34 times the square root of the waterline length in feet. For a 300-foot superyacht, the waterline length might be roughly 280 feet. The square root of 280 is...
For decades, traditional superyachts used a basic mechanical drive system: massive marine diesel engines connected to long, rigid steel propeller shafts that ran straight out the back of the hull. While simple, traditional shaft lines are incredibly inefficient on large vessels. The shaft must be aligned at a slight downward angle, meaning part of the propeller's thrust is wasted pushing the stern up rather than pushing the ship forward. Furthermore, traditional rudders act like air brakes in the water, generating continuous hydrodynamic drag every time the captain makes a steering correction. To bypass these physical limitations, modern 300-foot megayachts have abandoned mechanical shafts entirely. Instead, they use advanced diesel-electric pod propulsion systems, most notably ABB Azipods. Here is how the physics of an Azipod system work. Inside the hull, multiple high-efficiency diesel generators run continuously at their optimal RPM, producing raw electrical power. This electricity is routed through heavy-duty bus bars down to submerged propulsion pods hanging underneath the stern of the vessel. Each pod contains a high-torque electric motor sealed entirely inside a streamlined hydrodynamic housing underwater. The propeller is attached directly to the electric motor shaft, eliminating gearboxes, long shaft lines, and internal mechanical friction. Because the entire pod can rotate 360 degrees, Azipods act as both propulsion and steering. There are no traditional rudders creating drag behind the propeller. Furthermore, most Azipods feature a pulling propeller design where the propeller sits on the front of the underwater pod. This allows the propeller to operate in clean, undisturbed water, increasing hydrodynamic efficiency by up to 15 to 20% compared to traditional shaft systems. The operational advantages are massive. Because electric motors deliver instant torque at 0 RPM, a 9,000-ton superyacht equipped with Azipods can rotate in its own length without assistance from tugboats. Using dynamic positioning systems linked to GPS, the captain can press a button and the Azipods will autonomously hold the vessel motionless over a coral reef within inches without ever dropping an anchor.
Powering the ship forward is only half the engineering battle. The other half is keeping the guests on board from getting seasick. A 9,000-ton vessel floating on water is subject to 6 degrees of motion: heave, pitch, roll, yaw, sway, and surge. Of these, roll, the side-to-side tilting caused by wave action, is the most dangerous for comfort and structural stability. To neutralize roll, modern megayachts use active hydraulic fin stabilizers. These are massive wing-like structures protruding from the side of the hull underwater, often spanning 12 to 18 feet in length. Controlled by advanced digital gyroscopes, these fins rotate up to 20 degrees per second, generating dynamic lift in opposition to incoming waves. When a wave tries to push the port side of the vessel up, the port fin instantly rotates downward, generating thousands of pounds of downward hydrodynamic force to keep the deck flat. While active fins turn an unbearable storm into a smooth ride, they introduce another major drag penalty. When stabilization fins actuate, they function essentially like airplane wings generating lift. But according to the laws of aerodynamics and hydrodynamics, you cannot generate lift without creating induced drag. In heavy seas, active fins constantly adjust their angle of attack, creating massive turbulence under the hull. Operating stabilization fins at full capacity can increase total vessel drag by 5 to 10%. That means the engines must burn an additional 30 to 50 gallons of diesel every hour just to keep the champagne glasses on the dining table from tipping over. Even worse is zero-speed stabilization. When the yacht is anchored in a bay, there is no water flowing past the fins to create dynamic lift. To stabilize the ship at anchor, high-pressure hydraulic pumps forcibly flap the fins back and forth through stationary water, like giant paddles. This requires massive electrical energy. To run zero-speed stabilization while anchored off Monaco, the yacht's diesel generators must run continuously, burning up to 200 gallons of fuel per day just to keep the anchored vessel still.
Now let us look at the financial reality of keeping this machine operational. A 300-foot superyacht typically carries a fuel capacity between 60,000 and 100,000 gallons. In the maritime industry, purchasing fuel is called bunkering. Superyachts do not use standard automotive diesel. They burn ULSD marine gas oil, an ultra-low-sulfur, highly refined marine distillate designed to prevent injector fouling in complex marine engines. Let's run the numbers on a typical Mediterranean summer season. Suppose a 300-foot megayacht completes an ocean passage from Fort Lauderdale to Palma de Mallorca, a distance of roughly 4,000 nautical miles. Cruising at an economical pace of 12 knots, the journey takes roughly 14 days of continuous steaming. At 12 knots, the vessel consumes approximately 250 gallons of diesel per hour across main propulsion and electrical generators. Multiply 250 gallons per hour by 24 hours, and the ship burns 6,000 gallons per day. Over a 14-day passage, total fuel consumption reaches 84,000 gallons. At average global marine fuel prices, which typically range between $4 and $6 per gallon, depending on taxes, port fees, and location, a single transatlantic crossing costs between $336,000 and $500,000 in fuel alone. And that is just for transit. Once the yacht arrives in the Mediterranean, it enters guest charter operations. Even when stationary in port or anchored in a bay, a 300-foot yacht never truly turns off. The ship's electrical power plant must maintain continuous air conditioning for tens of thousands of square feet of living space, power high-capacity reverse osmosis desalinators producing thousands of gallons of fresh water per day, run refrigeration units, power